screen and take it from here. So you guys can see my screen, right?
Yep.
Okay, so just a quick disclaimer. I'm kind of, because I don't have like a lot of time, so I'm not going to go like in depth, like line by line, explaining what each part of the code does. What I'm going to do is I'm just going to show you on how to use the code and how to run it. So I'm going to start that right now. Because the thing is, when I made these algorithms, it was about like almost like a year and a half ago. So the exact detail I probably do not remember myself. So
yeah, that's fine. We can dissect it later.
Yeah. So let's start off with you know what I'm gonna do is, since this is all unorganized. Okay. So basically we have these three algorithms, right? And whatever are in these folders, I put them in the drive. So it's the same scripts. So we have X convolution, regression, and centric. And the common folder, these are just scripts that all three algorithms share. So I'm going to start off with the most complicated algorithm, which is X convolution. So you want to run this algorithm from X convolution main. So if I open this is what I get. So what you start with, the first step is this function, which is S equals trico vertices. And all this is getting is the map file, the 60x3 matrix of all the ISO coordinates. That's literally all that is. So I'm not going to bother opening that script because it's pretty self-explanatory. The second step is you're going to get the 60x1 array of intensities from the incident angle that you specify. So here you specify the azimuth, and here you specify the elevation. Now the stuff that is not trivial are these two things right here. So what these two things are, so the X convolution formula, along with the intensity and the ISAR coordinates, it takes in what is called the resolution and the depth. So basically what these are is, if I, for example, let me quickly pull up Desmos. Okay, so remember last time I was talking about how the way convolution works is you have a model curve and you have the actual curve, right? The actual curve is the intensity readings. And what you are doing is you're moving step by step in discrete steps, and you're taking the sum of products at each step. So basically, for our case, it's going to be an azimuth this direction, and an elevation grid. So the very I guess rudimentary way to do this would be brute force, like you do one by one by one by one, but that would probably take forever. Now, with the uniform case, I was able to find out, we were able to discover that the convolution curve, so like when you take the sum of products at each point, right, and you map that out onto a surface, that surface has one absolute maximum. So the important thing about the helpful thing about that piece of information is that we don't have to do it one by one. If we can find the maximum, then we can be close enough. So what I mean is, with the X convolution method, instead of going one by one, like one step at a time, what we do is we take one grid, right? Let's say this right here is our grid. And we specify a certain, going back here, we specify a certain resolution. All resolution is a number of ticks on the grid. So for example, I think if you start with 2, I don't remember exactly, but if you start with 1, it means 2 to the 1. If you do 2, it means 2 to the 2. So each time you up the resolution, you're doubling the tick marks. So for example, if this is our grid, right? 1 might be just the corner points, and 2 might be like the corner points and the middle points, and 3 might be between those points, and so on and so forth. You get the idea. So that is what the resolution is. Now the depth is the number of times you repeat the process. So for example, let me take this stuff out. So for example, if I go back to Desmos, so the idea with X convolution is if, let's say I pick a resolution of 3, right? If I pick a resolution of 3, I have this point. I start with this point, this point, this point, and this point, and then I have in between those points, and I have in between those points. So and if I pick a depth of, let's say 3, then we're gonna have 3 iterations. So for the first iteration, what we do is out of these points that I listed, that I showed you, I'm gonna take the sum of products, right? And I locate where the maximum sum of product is. So let's say out of all these points that I listed, let's say the maximum sum of products is like somewhere here. Got it? So what I end up doing is I take that whole grid, right? That whole grid with that desired resolution, and I squeeze it down to I scale it down to the, how do I explain this? I basically scale it down to the minimal distance. Are you guys following with me on that?
Yeah, makes sense.
Yeah. So like if my max point was here, I take my grid with that resolution and I will scale it down. And what is essentially happening is, let's say we had a point here, a point here, and a point here, and a point here, and a point here. Now that we have scaled down here, all those points get scaled down too. So essentially our resolution gets higher. Our resolution gets higher, but only within that, near the maximum. So the clever thing about this algorithm is we're not picking the highest resolution at once, and we're not going through every single point one by one. What we're doing,
just the maximum intensities, which is like the most valuable point.
Yes, exactly. So we start at a small resolution, we find the maximum in that resolution, then we iterate it, then we scale it down, and we repeat the process. And you can do that as many times as you want. But the one thing that I figured out is if you do like a resolution of like 4 or 5 and you do like a depth of like 6 or 7, that's pretty much good enough. It doesn't get any better than that.
Right.
Yeah. So if I open this script right here, so basically this script right here is basically explaining the process I was just describing to you. So for example, I believe this is the azimuth direction and this is the elevation direction. I might be wrong. And basically this is a depth. This is a number of iterations you're going to repeat. You're going to repeat scaling the grid. And this right here is, and notice how the grid dimension is specified by f+1. So basically, I can explain this to you. So this is the idea I was talking about. So n is the resolution, right? So this is a shrink factor. If you increase n, the shrink factor will increase. So if you do 90 divided by f, which 90 is from 0 to 90 degrees, it's a higher bound. This is a snap distance of the grid. So basically this distance gets smaller the higher you specify the resolution. And then the grid dimension is that +1. So basically you're iterating from each point of the grid, from the starting snap distance all the way to the end. And you do that for the azimuth and elevation. And so another thing to mention, so at each point you're basically doing the sum of products, and this is what it is. It's this function conv step that is doing the sum of products. So if I pull that up, so I remember when I was trying to drive this formula, it took me a while. I don't remember how I did it, but that is not important right now. What is important is the way I got this equation was by hand. I took the uniform model in terms of azimuth and elevation, and I convolved it to a hypothetical intensity model. And then by doing that, I was able to simplify to this equation. So basically, the clever thing about doing it this way, instead of generating, so previously when I first was making this algorithm, I generated the model curve like separately. I did it separately, and I convolved with the intensity readings one by one. But here, I'm not generating the model curve separately. What I am doing is I'm in fact just solving for as if it was the convolution was already done. So it's more like a function. It's like more like a mathematical expression now, rather than like a process. So that's what this is. It's basically, it's okay. To sum it up, it's basically the equation for the sum of products. If you're taking the uniform model in terms of azimuth and elevation and convolving it with the hypothetical intensity reading. So that's what that is. And you're doing that sum of products at each point on the grid. And then notice after each after you go through the grid one time, you're scaling it down. So this is what that iteration is doing. So after every iteration, you're scaling it down one more. So this is exactly what this process is. So the exact details, they're a little fuzzy. You can probably parse it. The key point to take away is this is how the algorithm works. You basically take a grid, specify resolution, find the max, scale it, and iterate. And that is the process. Okay, so that is pretty much for convolution. I'm gonna run it one time just to show you how it works. So I'm gonna do, are you guys with me, by the way?
Yeah. I think we're good so far.
Okay, so let me run this one time. If I run this, why is it doing this?
You gotta go to the folder.
Oh, it does this thing every time. Okay. So I gotta open trico vertices and run that first. So I go here. So basically I just gotta run this. If I run this, yeah. And then now if I do it. I gotta do the same for this thing, uniform simulation. So basically what this is doing, you're specifying an azimuth elevation and it's outputting the 60/1 intensity vector. So let me open that up and run that too.
Brad's got to take an input first.
Oh yeah, obviously. Okay. So let's go back to this. So, okay. All right, there you go. So let's say we specify like 65 and then negative 54. So let's say the desired resolution is, so just for purpose of explanation, I'm gonna start with a very low resolution and show you how bad it looks. So if I do like 2, and if I do like this like 3 times, the AOA error is actually pretty large. You see that? It's like 0.8 of an arc second, which is not bad, but still pretty large. Wait, actually, to be fair, I'm sorry, I apologize. This is not an arc second. This is a degree. So it's 0.8 of a, actually no, I should be careful with what I say. Here I have a sine d. Yeah. So this is 0.8 of a degree. So in our terms, our goal is 1 arc second. So that is really bad. But that's just to show you that's the best you can do if you start with a resolution of 2 and do a depth of 3. But let's change this. Let's run it again. Let's say we have like 75, and let's say we do like 67, and then we do desired resolution of 6, and let's say we do desired depth of 5. Look at the error. Look how much smaller it is. You see that?
Wow, yeah.
So, yeah, it's like a lot smaller now. So basically, the higher you go, I remember when I was testing this algorithm, there was an Excel sheet somewhere which I cannot find. I basically documented all the different combinations of iterations and resolutions, and there was like a point. There was like basically like a point where if you went any further, it wouldn't make a difference. So if I find that Excel sheet, I'll send it to you guys, because obviously you guys don't want to like tax your processor if you don't need to go that high. So yeah, so that is pretty much this algorithm. Now the other two are a lot more simple. So I tackle the hard one first. So the other two. So this is X convolution. Oh, there's other 2 things that I didn't explain to you guys. So if I go back to here, there's two things that are happening that you probably didn't notice. There's rotate isoc, right? And there's inverse rotate. Got it? Now, the reason why I did this stuff, because if, for example, let's look at this. Globe. If you take a look at this, right? Notice that near the North Pole and the South Pole, all the lines are converging, right? So basically, what that is telling us that if you have like an azimuth of like 30 and then an azimuth of like a negative 30, they're really close to each other because near the pole they're all converging. So if we did our calculations like near the poles, then there will be a lot of error basically. So a clever way I found to work around that is what I did is I found the maximum intensity readings, right? And I rotated the isoc such that the equator point was at the maximum. Because when we convolve it, right, it is imperative that the angle of arrival is gonna be around the maximum, right? So if you start near the maximum, then you're avoiding these extreme pole regions. Got it? So that is what I'm doing when I'm doing rotate isoc is, and if I actually open this, so let me open this. If I actually open this is exactly what I'm doing here. When I do find max index, I'm finding the maximum of the intensity readings, and then I'm rotating my isoc such that the equator point hits that maximum.
And it does that for any input, like
yes,
angles. Okay.
Yeah. So, and I do that every time before I run the convolution algorithm, because we want to be near the maximum because we want to be far away from the poles as possible. Yeah. And then similarly, if we're going to rotate the isoc, we have to invert the rotation that we did. So we're back to the right coordinates, and that is what I'm doing here.
I see.
This is basically the inverse of what I did here. And that is pretty much the convolution. And so going back, the regression and centric are a lot more easier to explain. So if I go to centric, so let's start with centric mean. And let me pull up this one, and let me pull up this one. So if I go to centric main, it's the same format, right? That's the same format as X convolution mean, but the only difference is, let me clear all this. The only difference is that we're not specifying the depth and we're not specifying the resolution because we don't need that. For centric, all we need is the intensity readings and the isoc coordinates, and that is good enough. That's all you need. And if you actually look inside the formula, so in this script, I put both formulas. I put centric and normalized centric. Whichever one you're running, make sure you comment the other one out. So that's what you want to make sure. So the difference between these two is, so centric, what this is, you can just tell by the formula that this is basically the center of mass formula. It's basically the weighted center. It's the, hold up. So if I go to, okay, so where did you guys keep the papers again? Was it in here?
Was it like presentation papers or like at the end of the semester?
Yeah, the end of the semester, those ones.
It should be in there, yeah, that folder.
What year was I? I always forget. Fall 2019. Okay. So basically this formula you see right here, this one, it's the weighted center. Is basically what this is. But you have to break it down because remember, going back to this R is a vector. So
right.
You have the X, Y, and Z.
Yeah, each dimension. Okay.
Yeah, and it doesn't get any more straightforward than that. You're recurring to as L, going back to radians, and you get the answer. Sorry, you're going to degrees and you get the answer. So this is pretty straightforward. So if I run this, of course, we're gonna have to deal with this crap again. So negative 78, 78, and then look at the error. Notice how it's much smaller than the other one, because the other one was like to the -7. But that is because the only reason it's much smaller is not because the algorithm is doing better. It's because the convolution algorithm, we didn't specify the optimal depth and resolution. So once you do specify that, you should actually be able to get something close to this. Yeah. So, and the normalized centric is the only difference between the centric and the normalized centric is you're normalizing the readings based on the I believe what it does is you take the maximum, right? So you take all the intensity readings, right? And you find the maximum and you divide all the other ones by the maximum. And basically now all your intensity readings are from 0 to 1.
Right. Makes sense.
Yeah. So that's what this is. And I believe when we implemented this approach, it was a bit faster, but it's not faster, sorry. It was a bit more accurate, but like not by a lot. So that's pretty much what centric is. So regular centric, normalized centric. Now last but not least, we have regression. Okay, so let me start with this. Again, same concept. Just like centric, regression only needs the azimuth and elevation and the intensity readings and the ISOC coordinates, and that is it. It doesn't need anything else. So if I clear this, and if I run this, I do -77, I do 88, and then again, ended up being smaller than the centric, but yeah. So this is pretty much the regression. And if I open the regression, so in regression, if you look here, this right here is essentially this formula. See that?
Mm-hmm.
And then with truncated regression, the only difference is you're finding all the points, you're finding all the intensity readings, which are 0. So basically the detectors that don't read any, they're on the other side of the hemisphere. They don't capture any light, and you're excluding them from the measurement. That's all it's doing. So you're truncating out all the basically useless detector readings that are not getting anything.
Right.
And again, by implementing this one, it was like a little bit better, but not by a lot. Yeah. So if I go to here, right? So these plots right here, they're basically the result at different signal to noise ratio of these 3 algorithms that I showed you. And this, so I make this bigger. The regression that was used here was truncated regression, and the centric that was used here was normalized centric, and convolution that was used here was X convolution. But the results that I was referring to last demonstration were these results. And as you can see, centric and regression actually perform the best at very high signal to noise ratio. But prior to the what's that word? Prior to the limit. So we'll call this the floor, the limit. Prior to the limit, convolution actually is neck to neck with centric. And convolution is neck to neck with regression, while centric is above. So centric is lagging a bit. And that's the same for the non-filtered and the filtered case. So by filtering the intensity readings, by taking 1,000 of the intensity readings and getting the average and then putting it into the algorithm, you shift the results about 30 dB to the left. So basically,
sorry, just to cut in really fast. I actually had a question about these results. Where do you guys modify or input the signal to noise ratio?
Yeah, so I was actually gonna get to you on that. So
okay.
On the Discord, I think I remember when I first messaged you guys about, I believe it was a Sunday when I uploaded all these files. Somewhere in my Discord messages, I said something about that we do have code. I do have code that that generates these plots and gets all the polar plots, and it can actually, it's basically like a test bench where you can iterate all 3 algorithms simultaneously for like, you can specify the number of trials, the number of samples, and all that. So that is a separate code, but fortunately I need to debug that code as well. So I do plan to post that, and I do plan to demonstrate that too. So that should be able to answer your question when I get to that.
Or kind of bouncing off of that, would that also include code to like filter it as well? I'm guessing.
Yeah.
For both. Okay.
So that's all in the same. Yeah. So the cool thing about that code is you guys can actually take that code and replace the sample filter with the Kalman filter. So that's a good thing about that code. But I need to debug it because I'm not gonna post anything that's like flaky.
Cool.
Okay,
Yeah.
so
I appreciate that. Thanks.
yeah. So for that, again, I can't promise because my schedule's all over the place, but I could say possibly this weekend. I'll keep you posted.
Yeah. Whenever.
But yeah, but that pretty much concludes the demonstration. Do you guys have any questions?
No, I think it was really straightforward.
Yeah. All right. Glad I could explain and help it. All right.
So Keenan, before this is over, you guys have been really like working with these algorithms, and you guys have like developed some code like in that direction. Do you guys have any questions in particular, and how do you guys feel about like familiarizing yourselves with this code and maybe adapting it to work with our Kalman filter versus continuing in your own directions and like trying to make your own programs based off of or like inspired by this? Where do you guys stand on that?
Personally, with the I feel like this explained it a lot more. Like I had a like at least with the regression, I had similar code for it. So I feel like it does, like it is very possible to like help him to implement with what we have. So I feel like a 7 or 8 out of 10, just in my, yeah.
I just realized the I and S are flipped. I should probably fix that.
Sorry, you just realized what?
I just realized the I and S, it's just a minor detail. The I and S were flipped. It was S and I.
Okay.
So you guys can probably fix that. Okay. All right. So I'll let you guys continue your meeting and I'll take off.
Sweet. Thanks a lot for this. We really appreciate it.
All right. Have a good one, guys.
Thanks, man. Take care.
Yep.
Okay, so that was pretty informative. I think we all got the gist of how all that's pieced together. I don't know if it's possible for code cleanup, Jackson. I would say try to. Well, we don't have the script to run or to be able to plot with the signal to noise ratio with the filter. That'll probably be a task for you, Jackson, when we get that, or if he ever sends that. Swap out whatever filter they were using before with the Kalman filter. Probably keep the one that they had just for like comparison's sake. But yeah, that'll be probably a task for you down the line.
Yeah, it looked nice.
I think the bigger question would probably be if there's a way, the issue that they had back then was, they plot all 3 because they work fairly well relative to each other. So after we get all that running and we're able to compare the outputs and how well they work together, probably the next step would be optimization, figuring out exactly which one to go with, because they both hit the floor that he was mentioning around the same time. So we'd have to figure out exactly what level of optimization we need to put on those things so that there's like a definitive algorithm that we're going to pick or use when the time comes to actually start implementing this stuff. But beyond that, I think, yeah, I would say Keenan and Andrew try run, pick one. UT Jackson, I recommended too because there's 3 of them. So just pick one, run it, try it with like a bunch of different, mess with the resolution, mess with the, at least for X convolution, try the different azimuth and elevations, see if you can. Okay, so Andrew picks X convolution.
Would you want
Uh,
us, sorry, I was gonna say would you want us to put in an Excel sheet, all this, right, like our trial and error, like all the values we calculate, I guess?
Yeah, that'd be great. Or just, keep in mind if there's any like funky errors or some interesting results that you get. But yeah, an Excel sheet with as much data as you can would be great. Hopefully sometime this weekend. Keenan, you can pick one out if you have time today or tomorrow. Try implementing that. You don't have to because I know it's pretty tight, pretty close to when you have to present tomorrow. But feel free to put whatever you want from today into the presentation tomorrow.
So guys, try to be free on Saturday or Sunday. Ideally, like late Saturday, early Sunday, because that's when we're going to be finalizing the paper and essentially like proofreading our draft. So, yeah.